Hey everyone, so we've talked about two different versions of the gravitational force law. One, in the limited case of a mass m, a height above the ground in the gravitational field of the Earth, right? That's given by this thing here. And then we've also talked about the more widely applicable version of this force law, which comes in the form of Newton's law of universal gravitation, which I have written here. Um, these two force laws are, of course, compatible with each other if you take the limiting case of Newton's law of universal gravitation, where you're, say, a small distance above the height of the Earth, it reduces to this version right there. But this one is more widely applicable. And now that we're talking about potential energy and conservation of energy, we should talk about the different forms that their gravitational potential energy can take as well. So this will be section 8-9 in your textbook. So chapter 8, section 9. The difference in gravitational potential energy for an object of mass m, a small distance along the y-axis above the ground, is given by m times g times that change in y, right? That would give you the difference in gravitational potential energy between those 2 points, right? Of course, this would be independent of x because gravity acts only in y. And now let's talk about this version here, the gravitational potential energy for the more general case of Newton's law of universal gravitation. So let's just set this problem up a bit. So here I have the Earth, and I have a radial vector extending out from the Earth, which I've called r hat. And we have an object that is, say, starting from some initial location out here, a bit of ways from the Earth, and that moves under the influence of gravity closer to the Earth right here. And of course, gravity is pulling on it as it's coming in, so gravity will do work on the object. The work that gravity does will not be, you cannot use this simple form here, right, where you take the dot product between displacement and the force of gravity, right, because this is not a constant force. Of course, the magnitude of the gravitational force depends on the distance squared. So as this object moves in closer to the Earth, the force is going to change. The force will get stronger as it moves in. So that means that the force is not constant across the displacement. So this form will not work for us. We'll have to use the more complicated form. And that would be this one here, force of gravity dot dl, where dl is the displacement element, right, along the displacement of the object. And of course, the gravitational potential energy then will be minus the work done by the gravitational force. So it will be minus this integral here. Let's put in Newton's law of universal gravitation then. So there's going to be a minus g m1, m2. We'll say that the Earth is mass 1, and this will be mass 2, divided by the distance between them squared. And this will be, right, the force of gravity is going to be in the minus r hat direction, right, because gravity pulls in. So taking this whole thing, there's a minus there in the front, there's this r hat, so we have this force in the minus r hat direction. And we will have to take that dot dl, displacement element dl. Now, of course, these two minus signs will cancel each other out. And r hat is going this way. dl is going in this way, this would be, so dl is going to be a small displacement element along this direction there, right? So r hat dot dl is just going to be dr. So you can think of dl, the displacement area, the displacement element, as being some radial displacement element plus some tangential displacement element. And this dot product with the r hat direction would pick out just that radial displacement element. And the tangential displacement element would be completely irrelevant for this calculation. So let's then do this integral. And I can take this, of course, from, say, the initial point up to the final point. So if I do this, I have, right, I can pull out the g m1, m2, and I just have then an integral dr over r squared from the initial point to the final point. So remember this rule, integral x to the n dx is equal to x to the n plus 1 divided by n plus 1. So I can do that. Vg m1 m2 times, well, this would be where n is minus 2 in our case. So I would have r to the minus 2 plus 1 in the numerator divided by minus 2 plus 1 in the denominator. And this would go from r final to r, I'm sorry, from r initial to r final. So I have this g m1 m2. I would have here r to the minus 1 power, or in other words, 1 over r. And then in the denominator, I would have a minus 1. So I have a minus 1 over r overall, going from r initial to r final. So what I have is g m1 m2 times a minus 1 over r final minus 1 over r initial. Or in other words, take this to be a plus. Okay. All right, so here I just rewrote this in a little bit nicer form. So the change in gravitational potential energy then depends on the product of the masses on big G, and then this the difference between the 1 over the initial radius and the final radius, which is much you might expect when you consider that the force of gravity depends on 1 over the distance squared, and then work is the integral of force over distance, right? The integral of 1 over a distance squared is going to give you a 1 over a distance. So that should make sense to you. Normally, you won't actually see it written in this form like this. Instead, normally, the reference, the kind of standard reference point to use is to take the reference point where UG is 0 at an infinite distance away. So usually you take then the limit as our initial goes to infinity of this change in UG, then this would be then UG at, say, our final minus, well, 0 would be the reference gravitational potential energy, right? Because take this limit here where our infinity, where our initial goes to infinity, right? That term ends up being 0. So normally you just see it written like this, where the gravitational potential energy, a distance r from the center of mass of a planet, is given by minus g m1 m2 over r. Of course, they're completely equivalent, right? If I want to do change in UG, right, it would be UG at r final minus UG at our initial. And that would be minus g m1 m2 over our final. Right here, I'm just plugging in our final to this formula here. Minus then the minus g m1 m2 over our initial. And these two things would cancel out. I could factor out the GM1, M2, and I still have this exact same formula that we started out with over here. So nature does not care about your reference point, of course, but this is just a kind of conventional thing to do. To take the reference point to be infinite and say the gravitational potential energy an infinite distance away is 0. Okay, let's apply this to a quick problem. So let's say you're on the International Space Station, you're a height h above the Earth, and you drop your hammer. Let's just say that you drop it from rest, and you want to know what is VF, the final speed that that hammer would have when it reaches the Earth. It will likely be a speed that would be deadly for anybody to try and catch it, say. Let's figure out using two different methods. The first one, the original thing that we talked about. And then the second one, we'll use the real answer, the one that we just found. So the initial kinetic energy would be 0 because you dropped it from rest. And the initial potential energy would be then mg times the International Space Station altitude. Okay, we'll just call that h for now. mg times h. And once you get down to the ground, then your potential energy would be, well, if we use this distance h up to here as the initial starting point, we might as well choose this as our reference point. So we can say that the potential energy final would be 0. Just like how the kinetic energy was 0 up here. So everything would then be converted to kinetic energy. Final. So let's apply conservation of energy then. We would have m times g times h, this 408 kilometers, would be equal to 1/2 times m times velocity squared for the final. We can cancel out mass. We would get that the final velocity is equal to root 2 times g times h. Plugging in numbers into that, I get about 2,830 meters per second for the final speed. All right, so this is a nice approximate answer here, 2,830 meters per second. But of course, exactly correct is the best kind of correct. And exactly correct in this case would be to use, rather than mgh for the potential energy, using the formula that we just derived. All right, here's the formula. In our initial state up here, we still have kinetic energy as 0, but now we're going to have an initial gravitational potential energy that will show up here. And we'll have a final gravitational potential energy down here, plus that same kinetic energy final. And plugging in my formula here, I can cancel out the mass of the hammer from each term. I can then take both of these terms over to the same side as I've done here, multiply by 2 to get rid of that 1/2, and take the square root to get rid of that v squared. And what I get is velocity is equal to root 2g times the mass of the Earth times this difference here between 1 over our final and 1 over our initial. And if I plug in numbers into that, note here that the final, our final, is going to be not 0, right? It's the radius of the Earth, right? Because it finishes up, so this would be 0, right at the center of mass of the Earth. The radius of the Earth, though, it would be where the final location is. The initial radius is not h, right? It is the radius of the Earth plus h, because this distance here in the formula is the distance to the center of mass of the object in question. So if I plug in these two numbers, you'll see that my initial radius is about 408 kilometers larger than the radius of the Earth. Putting those numbers in, I get 2,740 meters per second. So I get a number that's different by about 3%, and it's a bit lower. Still wouldn't want to catch this thing if it's falling, but it makes sense, right, that this value would be a little bit lower than this one over here, because in this approximation, we were assuming that this free fall acceleration due to gravity is g everywhere, right? It's g down here close to the Earth, which is a good approximation. It was also g up here close to the International Space Station, which is not that great of an approximation. So it makes sense that this one was a bit larger than the real answer, which we found here at the end. Now let's move on to talking about the escape velocity. So escape velocity is the velocity that you would have to launch a satellite in order for it to leave the planet and never come back. Okay, so obviously if you launch a satellite out some distance, it is always going to feel a pull, a gravitational pull from that planet, right? This is saying, let's find the minimum speed at which we could launch a satellite such that it would actually escape to infinity. It would never stop, turn around, and fall back towards the planet. Okay? So let's find the minimum speed at which you would have to eject a satellite such that it would leave the planet and never turn around and fall back towards the planet, even if it never encountered another body, another gravitational body. Okay, so let's say that our probe then is, so here's MP, the mass of the probe. ME is the mass of the Earth. The initial radius at which this, at this location here is going to be the radius of the Earth. And what we need then is, in our conservation of energy equation, a kinetic energy initial that is great enough such that we can get the kinetic energy initial plus the potential energy initial to equal the enough energy to escape the gravitational pull. Okay, so let's just think about this. The object is supposed to escape to infinity, right? But it's supposed to do so with as little speed as possible. So we want just enough energy put in initially such that it makes it to infinity, but it doesn't have any extra kinetic energy when it gets there. So that would be 0. The potential energy final is also going to be 0 because remember, we chose as our reference point, r goes to infinity and UG then goes to 0 at r equals infinity. So what we need is a kinetic energy plus potential energy initial equals 0. So the initial potential energy is going to be this from our formula here. Oh, this is embarrassing. That's what I meant. Huh. Okay. All right. Now, since the gravitational potential energy is minus g mp me over r, and my initial radius is the radius of the Earth, then I can write minus g mp, mass of the probe, mass of the Earth over r for my initial potential energy and RE. And the kinetic energy initial is just going to be, this is 1/2 m mass of the probe times the escape velocity squared, right? That's exactly what defines the escape velocity, is that it's the thing that gives you enough kinetic energy initially to overcome the potential energy of the planet that is holding on to you. Right? These two things are going to be equal to 0. Now, just to say something about this, gravitational potential energy here is going to be negative, and this is pretty typical. It's a kind of binding energy is one way to think about it. This negative gravitational potential energy, that means that you would have to have a lot of initial kinetic energy, right, in order to break these two things apart, right, in order to get the satellite really far away from the planet. So a more negative potential energy means a greater gravitational influence from the planet at that point. All right, let's just do some algebra on this. So I can divide by the mass of the planet here on both sides, and then I can add the GME over RE across to the other side. Right, this M had gone away. Then if I multiply this by 2 and to take the square root, I will get that V escape is root 2 times big G times ME over RE. Okay, so if I plug in numbers into that, I get that for the Earth, this is about 11.2 kilometers per second. So that's the speed that you would need to achieve in launching a probe out so that it never comes back. Of course, is not specific just to the Earth, right? You could take root 2g times the mass of any planet over the radius of that planet, and that is the velocity required to escape from the surface of that planet. Notice, right, this looks very similar to the velocity for a circular orbit, right? There's just that factor of root 2. That's the only difference. All right, let's talk our way through one of my favorite active learning exercises. So this is a problem about a black hole. So a black hole is an object so massive that even light cannot escape its gravitational pull. Using this information, you can determine the radius of a black hole, which is also called the Schwarzschild radius, after Karl Schwarzschild, the first guy who figured this thing out. And that radius then will be a function of the black hole's mass, MBH. So a black hole is so massive that even light, which travels at the speed of light here, cannot escape. So what that means is, if we have a black hole here, right, nothing inside of the black hole can escape, not even light. So if we use that as the definition of a black hole, just some region where light cannot escape, then the boundary of such an object would be the place where the escape velocity is equal to the speed of light. Right? Once you get out to the point where you're far enough away from the ridiculous amount of mass, say, at the singularity of the black hole, you will eventually get to a point where the escape velocity is just equal to the speed of light, c. So, plugging all of those things in, right, c would be the escape velocity. The Schwarzschild radius, rs, would be the radius down here, and mbh would be the mass of the black hole. So, plugging those three things in, we have this. Just do some algebra here. Square both sides. C squared equals 2g mass of the black hole over rs. Now I was asked to find, right, the radius, the Schwarzschild radius, as a function of the mass. So I'll just multiply both sides by rs, divide both sides by c squared, and I get that Schwarzschild radius is equal to 2g mass of the black hole divided by c squared. All right. So this is the Schwarzschild radius in terms of the mass of a black hole. What's interesting is that so we just solved this problem, right, using Newtonian mechanics. That would not necessarily be the correct way to solve this problem. You might think that you'd have to use general relativity, and turns out that when you use general relativity, you get the exact same result. So Newtonian mechanics is actually applicable in this case, because when you think about it, the escape velocity comes from this formula about what happens when you're an infinite distance away, right? So Newtonian gravity and general relativity become equal in that limiting case where you're, say, an infinite distance away from a mass. When you're really far away from a mass, then the two have to be equal to one another. So that's why you can use Newtonian mechanics even in this case of a problem with a black hole, where you would think that you might need to use general relativity to solve the problem. So that's kind of cool. Now, there's part B. It says the mass of the sun is 2 times 10 to the 30 kilograms. Imagine that if you had godlike strength and you could compact the sun's mass down into a smaller radius. What radius would you need to fit all of its mass into in order to make a black hole? And then what fraction of the radius, of its current radius, would that be? So let's just use the formula that we just found. This one here. The Schwarzschild radius is 2 times big G, which is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the black hole. So in this case, we're talking about a solar mass black hole. So 2 times 10 to the 30 kilograms is the mass of the sun, divided by the speed of light squared, which is 3 times 10 to the 8th meters per second squared. If I plug in all those numbers, I get something like this, or something around 3 kilometers. So that's interesting. 3 kilometers for a solar mass black hole. What is the ratio, say, of this value to the actual radius of the sun? Well, it's really small. It's something like 4 times 10 to the minus 6. So you would have to compact the mass of the sun down into a region that is about 4 millionths the radial extent of of what the sun is currently. So this would not be an easy task by any means. So if you found this problem interesting, I'm eventually going to make a course called Black Holes in Extreme Astrophysics, which I taught as a graduate student. I'm eventually going to make this a class here at MSOE. So if you want to learn more about stuff like this, you should look for that class. I think, who knows, maybe next year. All right, good luck on your homework. I hope you learned a lot about gravitational potential energy. Okay, last thing to say is I just wanted to define power for you and talk about it a little bit. So power is the energy transferred per unit time. So this would be section 8.8 of your textbooks. The other stuff that we were just doing was section 8.7. This is 8.8. At least in my class, I'm not going to do 8.9. Maybe in your class they will, but I won't. So power is the energy transferred per unit time. So if you have, so energy transfer is another way of saying work. Work is whenever work is done, energy is being transferred from one body to another. So we can express work then as, say, the dW dt. This would be the instantaneous power at any given point, the amount of the time derivative of work. Average power, let's say that you have a total amount of work done, W, and it takes an amount of time T to accomplish that, then the average power would be work over the time T. A better way to think about it is probably just the energy transferred per unit time. So when we talk about, say, the power of a light bulb, right? We're not talking about an amount of work done that translates to mechanical energy per unit time, but rather it's just the power is, right, the time derivative of energy, right? The energy that is output per unit time. And when you think about this in the case, say, where force is constant, when force is constant, right, work is equal to F dot displacement. Okay, if power is the time derivative of this, in this case where F is constant, we'll have power equal to dW dt, or in other words, it's equal to d dt of force dot displacement. Now we said that F was constant right from the outset, so the force is going to be constant, right? So constants aren't affected by the derivatives. So instead, you'll have this d dt of the displacement vector there. And of course, the time derivative of displacement is velocity. So you can write then that force dot velocity, force dot product with the velocity vector, would give you the power of a constant force acting over a displacement d. One last thing to say about power is that we can define efficiency then in terms of power. Efficiency is going to be the power that is output by a system divided by the power that is put into a system. So let's say I'm talking about a microwave here. The power put into the system would come from, right, the outlet. It gets plugged into the wall. The power that is output by the system would be, well, the amount of heat transferred per unit time, say, as you're cooking something. That would be one way. That would probably be the most accurate way to quantify the output power. Who knows? Maybe the on the box for a microwave, they might talk about the power output as the radiative energy per unit time, whether or not it gets absorbed by food. There'd be two legitimate ways to talk about the power output here. But if you take the output power divided by the input power, that would give you the efficiency of, say, an engine or a device of any kind. So these are the things that are important for you to know about power.